All right, and so in this video, we're going to be looking at writing the parametric equation of an ellipse. And we're going to talk about the standard way that we do this, and then also some things that you can do to vary your parametric representation. So let's think about our standard equation in rectangular coordinates. And we're going to stick with things that are centered at the origin. You can, of course, shift everything off the origin by just simply adding your center, adding your constants to your parameterization. We'll talk about that a little bit briefly, but this is our standard equation. Now, unless you're trying to find the focus, you don't really care whether A and B are bigger than each other or not. The longer direction will be your major axis, the shorter direction will be your minor axis. Typically, when we're doing this with rectangular coordinates, we try to treat this as if the A is always the longest. And so in this example, it would be horizontally oriented, it would be longer in the x direction. And if you flipped it, you had x squared over b squared plus y squared over a squared, that would be representing the fact that it's longer in the y direction. Again, this doesn't really affect us when we go to parametrizing because we need one of A or B to be bigger in order to find our focus and know what axis it's on. But when we're doing parameterization, we're not necessarily doing that. We're concentrated more on just the general outline of the outside of our function or our graph. So I'm just going to treat A and B as if they're just constants and they're scaling in that particular direction. So the standard way to do this representation is x is equal to A cosine theta or t when we're doing parametric forms, and y is equal to b sine t. Now, as I said, you can shift everything off the origin if you really need to. And so in this case, you would just modify this with A cosine t plus h, and y equals b sine t plus k. So all of the examples that we're going to talk about from this point forward, where they're going to be centered at the origin for the sake of simplicity. We're going to worry about one adjustment to our parameters at a time. But in principle, you can always make all of these adjustments that we're going to talk about to your ellipse in order to get it to behave in a very particular way. Now, given our standard parameterization, the one that we came up with here centered at the origin, this parameterization has some particular properties. And so we're gonna look at those properties and then we're gonna tweak them. So the first thing is that this function in time, you have an orientation, like which direction are you going around the thing, which you don't have to worry about in rectangular coordinates. But here, the standard orientation is counterclockwise. The graph starts at t equal to 0 at the point a comma 0. So it's starting on the positive x-axis. And then it goes counterclockwise. So it goes from the positive x-axis to the positive y-axis. So from A0, it goes to 0b, and then it goes to negative A0, and then it goes around to 0, negative b, and then back to A0. So that's the order that it goes around the graph. The second thing is that it takes the interval 0 to 2 pi to go around the ellipse one time. Again, this is the standard parametrization. Now, there are things that I can do to change aspects of this parameterization. So, for example, suppose I want to change the starting position. So maybe I don't want to start at the positive x-axis. I want to start at the positive b-axis, the positive y-axis. So what you can do is add a phase shift to the angle. So the phase shift can get you to actually start anywhere on the ellipse you want, as long as you can calculate the angle where that is represented. So if I wanted to start at the positive y-axis, what I can do is that's 1/4 of the way around the ellipse. And so I would add pi over 2. And then y is equal to b sine t plus pi over 2. I have to add the same phase shift in both coordinates. And if in doubt, you can double check. Now this, by plugging in the value 0 and seeing what coordinates you get, this cosine of pi over 2 will get you 0. So your first component is 0. Plugging this in will get you sine of pi over 2, which is 1. So that'll get you b, that'll get you 0b. So that's the positive y-axis. And by just adding this phase shift, you are still going counterclockwise. And you are still circling the entire thing in an interval of 0 to 2 pi in t. Okay, so nothing else has changed, just the orientation, just the point at which you're starting. So if you want to start on the negative y-axis, the negative x-axis, you could add pi to both of these. If you wanted to start at the negative y-axis, you could subtract pi over 2 from both of these, or add 3 pi over 2, whichever you prefer. That's still going to change your starting point, but not change anything else. Now, there are identities that you can use to simplify and reduce this. So I'm not going to worry about those, but phase shifts can get you to start any place on this ellipse. Another way to change the orientation is to add a negative to one of these components. So a cosine t. In fact, you would just replace it with negative t. And then actually, let's put parentheses around this just so that it's super clear. And then y is equal to b sine negative t. Now, the result of this, again, the orientation, by making t negative, you're going to go, instead of clockwise, instead of going counterclockwise, which is the standard math orientation, now you're going to go in the reverse direction. You're going to go clockwise. Now, the way that this affects the result is that cosine is even, and so it doesn't actually change, but sine is odd, and so the minus sign can come out. So this is again, simplified result of this. Essentially, you're just changing the sign of the y component, and now you're going to go clockwise instead of counterclockwise. Again, everything else about this from the standard orientation will stay the same. You start on the positive x-axis, and now you take 0 to 2 pi to go around. The only difference when you make this change is that you're changing from counterclockwise oriented to clockwise oriented. Now, you can change both the orientation and the starting point at the same time. if you want it to start at the positive y-axis and go clockwise. And to do that, that's simply to switch your sine and your cosine. So this would become A sine x sine t, and y is B cosine t. That will have this double effect in that you will start at 0b, but you will go clockwise around the ellipse. And again, I've left the A's and B's positioned in the X and the Y coordinates the way they were so that you're not changing the shape of your ellipse, you're only changing the orientation and starting point. Now, the last thing, we've changed the orientation, we've changed the starting point, we've changed the center. The last thing that we want to change is how long it takes to go around the ellipse. And so that's going to depend on the period of our sine and cosine functions. Typically, those are 2 pi. But if we want them to go faster, so complete a circuit in pi units, instead of 2 pi units, then we would have x is equal to a cosine 2t, and y is equal to b sine 2t. You have to scale both of them by the same amount. So this will make it go faster. So by the time t is equal to pi, you'll be evaluating cosine of 2 pi. So that's going all the way around. If you want it to go slower, so complete a circuit in 4 pi units instead of 2 pi units, then you would reduce. So x would equal to a cosine 1/2 t, and y would be b sine 1/2 t. So now, again, it's going to start at the same place, but now when you go t equals pi, you're going to multiply that by 1/2, and so the angle, the cosine evaluated, will be pi over 2. So you've gone pi, but now you're actually only evaluating it at pi over 2. So you're only a quarter of the way around the circle. It's going to take you twice as long to get twice as many values of t to get all the way around the circle. So when you see a problem, it's going to tell you you want to do the ellipse in an interval of 0 to pi, you have, or 0 to 4 pi, something other than 0 to 2 pi, you're going to need to scale your t parameter so that it goes faster or slower in order to complete the circuit in 1 unit. Don't ignore this, because later on, if you're asked to evaluate it, particularly if you're doing calculus and you have to find the slope at a particular point, you're going to have a problem, because if you haven't scaled this, you're not completing it on the same interval. The slope will be wrong. So any further calculations will not be correct. Now, as a caveat, you may remember from doing transformations that transformations, scaling and shifting at the same time, they're going to interact with each other. So when doing combinations of these things, it's always a good idea to plug in a point or two, just to make sure that it's doing what you expect it to do, that it's interacting with each other in the right way, so that you're applying them in an order that is appropriate to get the effect that you want. So just kind of keep that in mind, particularly with parametric equations. Sometimes these behave a little differently than when we're dealing with X and Y. And so it's always just a good idea just to check on the interaction between these things. Test a point to make sure that something like t equals 0 and maybe t equals pi, and just to make sure that it's behaving in the way that you're intending it to behave when you start putting these things in combination.